Hello, I'm Paul Beckwith, and I'm going to continue my discussion of a new paper that has come out with the lead author, Jennifer Francis, who I'm sure you'll recall about 2012 put together a very significant paper with her colleagues on the jet streams becoming slower and wavier, causing extreme weather events in different parts of the planet. Stuck weather, persistent weather, with the jet stream ridges stuck over one location with heat waves and drought underneath, and the troughs in another location with very big storms, and the north-south distance that these jet streams traverse is becoming ever greater, such that in fact the ridges have been seen to go right up to the Arctic, the North Pole, and the troughs have gone down to the equator and actually crossed the equator, meeting with jet streams from the southern hemisphere. The paper is called Measuring Weather Whiplash Events in North America, a new large-scale regime approach. Okay, so I discussed some of the basics, some of the basic ideas in the previous video, and in this video I'm going to continue on looking at the data. So basically these are the images that we have. So if you take all of the data from all months from 1948 to 2019, okay, take the pattern that we're in on each day in this large time period of, what's that, 52, 70 odd years. Okay, each day, that's a lot of different days. The weather is in one of these modes, and that's so these modes are all generated by a neural network to represent the different possible states of the atmosphere. And we have this is annually. This is both in winter, summer. So and the numbers here. This pattern here, very, very warm Arctic anomaly, happens 15% of the time in the winter and 9% of the time in the summer. So all of these modes happen in roughly equal percentages of the time in that whole data set. In the summer and in the winter, we get preferentially this mode. We used to have this mode, so it's common. Or you have a mode like this, where you have a ridge here, very warm air, and then trough here, very cold air, or a trough here and a ridge over here. So these are the most these are furthest apart. So the term used is the Euclidean distance between these guys here is very large, same as from these guys here, whereas these modes here are much closer together. Okay, so that's the key point. So let's look at the findings of the data. Okay, so this shows you frequency histograms, where the number of samples or the number of days is in this axis, and this is the mode. So we've got the 12 modes, okay, and they're labeled here 1 to 12. Okay, so just keep that in mind, and we've got the 12 modes. Now if we're in mode 1, for a long duration event, so four or more days in mode 1, then this is the histogram that is important. And 2 days later, the pattern can stay in the same mode, so that's an even longer duration event. One stays in mode 1, but most often, one will shift to mode number 3 or mode number 9. Okay, so one will shift to mode number 3 or mode number 9. Okay, so in other words, this whole thing will rotate like this, or it will rotate to the right like this. Okay, most often. So this is how you read the data. So if you look, not much happening in a lot of these. If you're in mode number 3, it will shift most often to modes 1 or 4. So if you're in mode 3, it will shift to 1 or 4. It'll get weaker, or it'll flip if you like. Okay, so you get the idea. I'll do some more. If you're in mode 4, it most likely shifts to mode number 3. Right? So let's go back. If you're in mode 4, it shifts to mode number 3. It mostly weakens. Okay, and this is, if you're in mode 9, it mostly shifts to 10. So if you're in mode 9, it mostly shifts to 10, it weakens. If you're in mode 10, it shifts to 9 or 12. Mode 10 shifts to 9 or flips. Okay, so the colder air is up there, warmer air is down below. And if you're in mode 12, this is a very interesting distribution. You shift mostly to significantly to 4 or 10. Okay, so 12, it shifts to 4, flips this way, or it shifts this way, 4 or 10. Okay, so this shows you how the patterns of the atmosphere are changing. Now this is an interesting thing. This is the frequency of occurrence of the days of in each node between the change from 1961 to 1989 to what happens from 1991 to 2019. Okay, so 2 time periods. It's what's happening to these modes. So again, we refer here. So these are all of the modes where they look at the spatial position of them. And what this is showing is that on an annual basis, we get the big X is statistically significant to the 95% level, and the little x to the 90%. Okay, so there's a big X here. We get a large increase of days in this particular annually in this mode here, and we get a large decrease in this mode. We get a large increase in this mode and this mode. So let's have a look at where those are. In this mode and this mode happen a lot more than they used to happen. And this mode and this mode decrease a lot more than they used to happen. There's a lot less, the Arctic is cold a lot less of the time, and we also get less of this pattern. Okay, with a weakness, sort of weak, intermediate pattern. Okay, so that's what that's showing annually. Now we can divide it up into winter and summer. So in the winter, we have a lot less of this mode here. So we don't have a very cold Arctic in the winters anymore, much less of this mode. And we get more of this mode in the winter. So we get more of this sort of pattern in the winter. Very, warmer over in this area in winters, colder over in this area. Okay, that's what that is showing. And notice that not much happens there. In the winter, the Arctic is in darkness, so we don't get all of that tremendous heating in the winter. It is warmer than normal, but the anomaly is shown to be small here. Again, this is showing the change from 61 to 91, this time period, to 91 to 2019. In the summer, however, we get some big changes. We get a lot more of this mode and significant, and these 3 modes there's a lot more of in the summer. So we get a very, very warm Arctic, nominally warm Arctic, or very warm over Hudson's Bay area and cold out on the Pacific side. Okay, so that's happening in the summer. And we get a decrease of these modes here along the bottom. So we get a decrease of this mode and this mode and this mode. Okay, so this is in the summers. The Arctic doesn't stay cold. Okay, so that's what that is showing. And now this is showing the temperature anomalies in the positive direction, in the negative direction, and precipitation for each of the different modes. And this is in the winter, so January, February, March, temperature and precipitation extremes. So this is air temperature anomalies being positive. So basically that's no surprise when we're in this mode here. Okay, this is the number of days that are warmer than, I think it's plus 1.5 sigma. They're exceeding the temperature average by 1.5 sigma. And so you can see with each of these modes, you can get the temperature distribution. So you see where the reds are, those are warmer temperatures. They correlate to warmer temperatures here. The cold temperature anomalies here, correspond to these modes here. But again, these modes here with the cold Arctic are happening less and less frequency. With less and less frequency, and this shows the rainfall distribution in the different regions. Okay, this is done for the winter. Okay, and now it comes for the summer. The same sort of data is shown for the summer associated with these patterns. So, we're in this mode with, these are the days with warmer temperatures at the 1.5 sigma level for this pattern here. Okay, and it's in the summer. Now it's associated with the second number, the second percentage. Okay, so you can see lots of different things from those. This is well worth downloading this paper. Just Google the title, open the paper, and have a look at these. Now here's how the weather whiplashing events are changing per year. So we're seeing a significant increase of this. Now each of these graphs corresponds to the position of the node. So this guy here, the first row, the third column, we're getting an increase over time to present day. So this mode is happening more and more often. That's what that graph is showing. And this one here is happening less and less often. The solid the dark red lines are the most statistically significant. So we're getting a drop of that mode, and of course that mode is a cold Arctic, so that's no surprise there. And we're getting some weaker movements and correlations. This mode's also increasing here, and you can refer back to here. So we're getting this mode here where the Pacific's very warm, and this type of thing, when this happens, we get the Pacific warm pool, or the ridiculously resilient ridge, okay, if you call those terms. Okay, and this is the difference in January, February, and March. So this is the winter difference. We're getting, so we're getting a lot more of these and a lot less of these in the winter. So we're getting a lot more of these and a lot less of these in the winter. Again, we're getting this ridiculously resilient ridge carrying into the winter. And then in the summer, July, August, September, we're getting less of these two modes and more of this mode. So we're getting less of this and less of this, and we're getting more of this. Okay, so you can play around with these and see what's going on. And then this is now what's being done is what's going to happen in the future. When we run the climate models, what's going to happen in the future, and what it's showing is this is in January, February, March. We're going to get way more of this mode, way less of this mode, and also more of this mode. So we're going to get a lot more of this pattern, a lot less of this pattern, and also more of this pattern. Okay, and in the summer, July, August, September, we'll get slightly more of this mode and more of this mode. This is similar to this, and we'll get a lot less of that mode. Okay, so this paper, I highly recommend that you have a look at it, because it really gives us a lot of information about these so-called weather whiplashing events. And these events are very important because they're hugely disruptive to society. They're hugely disruptive to our agriculture, and they wreak havoc on crops. They wreak havoc on society. I mean, the drought to flood to drought, or heat to cool to heat, and all of those things cause a tremendous impact on infrastructure. Okay, thank you for listening.